Okay, so you guys, and so the mic is okay. I'm not using my regular mic because I have the camera set up. I might switch to it a little bit later. So I want to introduce the last lab of the semester today, and I will talk more about it next week. We actually have, what, 2 more lab meetings after this one? If I remember correctly. So my guess is the last lab I might use for catch-up time. We'll see. Okay. So this is the LRC lab. So let me do the following. Oops, that's not what I want. Talk about the experiment. The circuit is actually pretty simple. You're just going to connect a resistor, capacitor, and inductor in series. And the goal is to study LRC circuits, pretty much almost everything you can about the LRC circuit. So this lab is somewhat data intensive. So you're going to be collecting quite a bit of data. And you're going to be doing quite a bit of analysis. So this is when you do want to get started early. But like I said, collecting the data should be pretty easy. So you will be using the one 1 millihenry inductor. It says 10 millihenries, but it's actually 1 millihenry. Okay, so use the 1 millihenry inductor. There's a resistor that's gray colored. And let me see if I can pull it out in my bag. So I'll show you the resistor in a little bit. You're going to be using like a 1 ohm resistor in this lab. So that helps make the quality of the circuit a decent value. And you'll use a 4.7 microfarad capacitor. You're just going to connect them in series. And let me see if I can show you the circuit real quick. Okay, I'm going to have to rotate my... I have the circuit right over here. Let me try to raise it. But you can't see the inductor because I'm using an inductor substitution box, so I can actually change the inductance. So basically, it's just what's missing here is the inductor. It's in series, but it's below the circuit. This wire, the yellow wire, and the green wire come from the inductor. But that's essentially my circuit. The capacitor, resistor, and the inductor is below. Okay? And then you'll use your signal generator. So I ought to warn you that my signal generator is different from yours. My signal generator, I had some issues with it because the one I used over the summer to set up this experiment maxed out at 25 milliamps. Oops. So mine maxed out at 25 milliamps, but yours might max out at a different value. So that maximum current can play a role in your lab. You don't want to go above the maximum value. Okay? Because otherwise your voltage will just be flattened out. All right. You're going to set the voltage to the circuit. What you want to do is the following. You want to set up your LRC circuit. That's not good. Hold on a second. This, you're going to be measuring voltages here. You're going to have the scope here. Okay, so you have the scope here. You'll have an ammeter in your circuit. And you're going to be measuring voltages. These are all going to be RMS values. Because you're going to be measuring them with the multimeter. Okay? So all the data you're going to have is an RMS value. And you'll be measuring with this guy. Okay, so what, or the other one, I'm sorry. So this will probably be this guy, the bigger one. And then you'll be measuring voltages with the little one. You just got to go from one to the next to the next. Okay. Normally when we're doing this in the lab, we have 3 set up for you. So you can hook up 3 of them and then a 4th one for this guy and a 5th one for the power supply. This lab, usually when we're in class, we'll have at least 5 or 6 of these next to your setup. So you use them all. But since we're doing it online, and we can only give you a couple meters, you're going to have to move the meter from one element to the other. So you want to wire the circuit, but you need to determine the resonant frequency of your experiment. And so you're given what C is, and in fact, what I would do, since this meter can measure capacitance, I would actually physically measure it. It says 4.7 microfarads, but it might be off a little bit. So I would measure it. And then we have no choice with the inductor. It's 1 millihenry. So 1 millihenry here, around 4.7 microfarads here. Calculate what F naught is. Set the signal generator to the resonant frequency, because this is where you're going to get the maximum current, approximately. Okay, it should be close. So set the signal generator to this frequency, and then adjust the voltage. Adjust the voltage so that you don't maximize, you don't go beyond what the signal generator can give you. Now, in the lab, it says 25 milliamps because that's, when I use my signal generator, that's all it allowed me to give. But yours might be different. In fact, the manual says 250 milliamps, which I'm surprised. Okay, but mine would only go to 25 milliamps. So you want to adjust the voltage so that you don't max out the system. So the maximum current's at resonance. You want to adjust the voltage of the signal generator so you don't go beyond the maximum value for the signal generator. Okay. If it's a volt, then it's fine, use a volt. If it's half a volt, then use half a volt. That's fine. Okay. And measure that current. Measure what the value is of that current. Of course, you want to start at the highest setting on the multimeter. And if you can go down one, then go down one. Okay. You do want to get a lot of sig figs when you're measuring current. Especially for this lab. You want to get as many sig figs in measuring current and as measuring voltages as you can. And then you have to use the same current setting throughout the whole experiment. So my question to you is, why do you have to use the same current setting throughout the whole experiment? What do you think?
Well, because that wouldn't affect the like inductance and capacitance if you change, or not the capacitance, but it affect like the inductance discharge time or whatever, right? Wouldn't it?
Well, yeah. The thing, and so the thing about that is that you're going to miss you're not going to see the transient response. The transient response is so fast in the circuit, you're going to miss that. So what we're looking at on the scope, what you see on the scope, that's the steady state case. So you won't miss the train. You're right in that, but you won't see the transient response. So this resistor that I'm showing you here, that you're going to put in the circuits, the gray one, is about 1 ohm. The meter, when you set it, if you set it to a particular setting, the meter resistance might be several ohms. That's going to affect the resistance of your circuit, and that will affect the quality of your circuit. Okay, so that's why you don't want to. If you change scales, you're changing the total resistance of your circuit. You're changing your entire circuit during the middle of the experiment. You don't want to do that. You want to keep it the same. So that's why I'm saying, go to the resonance frequency and measure the maximum current. You actually want to set your maximum current because you don't want to peg your power supply. And then use the same current setting on the meter throughout the whole experiment. Once you've done this, then all you got to do is you vary the frequency and measure V sub L, V sub R, and V sub C. Your goal is to get this graph. You're measuring RMS value. You want to get this graph, and whether you plot this as a function of frequency or omega, I don't care. You want to get that graph. So you're going to need at least 25 data points. So let's say this occurs at 1500 hertz. Okay. You know, how many data points should you take? Well, you don't have to go to 5000 hertz. Okay. And in fact, it's possible that these multimeters are not reliable at 5000 hertz. So you actually don't want to go that far out. You want to go, basically what you want to do, you want to be able to pin down the peak of that graph. So how would you pin down the peak of that graph? Well, first of all, I would start making the measurements at the peak. Okay. And near the peak. That's one thing, one choice you can have. Or you can start, at the bottom, maybe down here, and then go down to here, and then take a few more points further out. You want to pin down this peak, so when you get close to the maximum, you probably want to vary your signal generator by maybe 10 hertz. If my peak is at 1500 hertz, I would take a data point at 1490. I would take a data point at 1480, 1470, 1460. Okay? And then I'll do the same thing above. You don't want, so you got to think about what you're doing here, and you got to observe what's happening. You don't want to make your step size and the frequency too small so that the meter reading doesn't change. You want to make the step size small enough so that the meter reading still changes. Okay? Because if you make your step size too small, if I go by 1 hertz at a time and the current reading doesn't change, that's useless because you're beyond the resolution of the multimeter. You want to get as small a frequency step up here as you can, but it can't be too small. because you want to actually measure a change in current. You don't want to go beyond the resolution of your meter. Does that make sense? So you have to think about how small a step size you can make in your frequencies. When you're further away from the peak, you can go in increments of 100 hertz. So if this peak was 1500 hertz, I probably won't go beyond 2500 hertz here. I probably won't go below 200 or 300 hertz here. Okay. I don't have to go down to 0. It's going to be too hard for you to go down to 0. But I probably, if this is my peak, I probably wouldn't go maybe below 300 hertz, 200 hertz, and I probably wouldn't go above 2500 hertz here. And in fact, the last two steps might be 250 hertz increments. What are we here? You want to make them as small as possible within reason. The multimeter, the ammeter has to change value. Otherwise, this graph is going to be cut off. Your graph will look like a step function. You don't want that. You don't want a step function for a graph. Okay? So don't do that. You don't want to make your change in frequency very small near the peak. You don't want it to be too small. Does anybody have a question on that? There's little things you got to think about in doing this experiment. I kind of left it open-ended because I want you to experiment with things. Okay, I want you to experiment with what the voltage would be. I want you to realize that the signal generator has a maximum current it can put out. You're not going to put 10 volts into your circuit because your signal generator won't be able to supply that current. So I want you to optimize it. And once you've optimized it, then you can collect the data. But this is one of many graphs you have to graph. But this is the graph for which you're going to do most of the analysis on. So let me show you the graphs and the data you have to calculate and stuff. So let's say you collect 26 data points or 27 data points. Let me show you the data table. And I didn't draw in all the rows. You have to add the rows. Oh, by the way, notice that you have to write the purpose of the experiment in your own words. Don't forget that. So here's a data table, and I didn't draw in all the rows. You have to add the rows yourself. So if you don't know how to add rows, you can always go to the bottom row and just hit return, and it'll add a row. And then, by the way, try to keep your data table all on the same page. I would keep the whole data table on the same page. So you're going to measure, you're going to list the frequency from the signal generator. Then you're going to calculate omega from it. You're going to measure V sub L, V sub C, and I. Then you're going to calculate X sub L because V sub L over I is X sub L. X sub L divided by omega is L. So you're going to calculate this one. So maybe I'll color the backgrounds. That one's calculated. That one's calculated. This one's calculated. That one's calculated. And then from V sub C over I gives you X sub C. See, that's calculated. And then you're going to calculate this guy. And then you're going to calculate this one too. So all those columns, you're going to calculate something. Okay? Now, how many rows is that? Oh, how many columns? 1, 2, 3, 4, 5. So 6 columns. And if you have 25 data points, if you do it by hand, you have to use the calculator about 150 times, which is not worth doing with a calculator. So I expect you to use Excel. So I'm going to open up Excel. And let me show you some things with Excel you can do. You really should use Excel for this. I'm going to take this table, by the way, and I'm going to copy it. And then I'm going to go to Excel. Oops, didn't like that. And I'm going to paste it in the Excel document. Just 1 second. There's my data table. Let me blow this up a little bit. It's too much. Okay, so let's say I have some frequencies here. 100, 200, 200. So let me just show you one thing you can do with Excel, by the way. Let me highlight these 2 columns. If I drag this down, I can just copy and paste all the values. I'm going to have to calculate omega. So to calculate omega, I go to the, I'm going to show you how to do a calculation. I hit equals, then I type 2 star pi with parentheses, star P5. I think it didn't like pi. I forget the name for pi already. I'll do 3.14. Oh, it's A5, sorry. Let me go back and let me put pi in again. I messed up, sorry. Okay. So I took 2, let me blow this up. I won't blow it up. I took 2 times the function pi I just shoot it. Let me write it again. 2 times the function pi times cell A5. And I didn't put the equal sign because otherwise it would have calculated it for me. That's what I did here. Then all I'm going to do is drag this down. Oops, I'll do it one more time. And then it calculated omega for me. I'll have values in here. I'll have values in here. And by the way, you can change the units if you want up here. You can make these milliamps, however you want to do it. Let me just put a value here. Okay, So I want to calculate X sub L. I type equal. I type it's voltage over current. So I'm going to take the voltage in cell C5 and divide it by the current in cell E5. And then I'm just going to drag this down, and it'll give me the value. So I highly recommend that you use this. Now to calculate Z, you can just take the power supply voltage divided by I. But you want the RMS power supply voltage. Okay? This last column is the RMS power supply voltage, which you can measure with the multimeter. So measure VRMS while also monitoring the instantaneous voltage as a function of time. And so you can calculate everything really quick with this. You guys have questions? Concerns? You guys can hear me, right?
Yeah.
Okay, I just want to make sure you can hear me, okay, because no one's saying anything. Okay, so what are you going to do with this data? So now I got to switch views. Hold on a second. Let me go back to the document. Oops, not that one. And let me show you the plots you have to make. You have to make 3 graphs with a total of 6 plots. So you're going to plot the impedance and reactance on one graph. You're gonna plot the total impedance on your graph. You're gonna plot the capacitive reactance on your graph, and you're gonna plot X sub L on your graph. Okay, I'm not sure why 300 hertz is there. So that's one graph. So 3 plots on that graph. No curve fit. Then, oops. Here on the second graph, you're going to plot IRMS versus frequency, or omega. Either one. Probably omega. It'll make it easier for you to curve fit. This is the one where you're going to do all the analysis. So on this graph, you will do a curve fit. And you will do a lot of analysis on it. You will find the full width at half maximum, because that's related to the quality of the circuit. And I'm going to talk about that next week. And in the third graph, you're going to plot V sub L and V sub C as a function of frequency. And the idea is to extrapolate to 0 and high frequencies so that you can see which element dominates at low frequencies and high frequencies. That's what that graph is for. So the only one where you're going to do a curve fit is this one. The other two, you're just going to graph them. Don't have a line on these graphs. Just connect the data points. I'm sorry, don't connect the data points. Plot the data points for XZ and X sub C, X sub L, and Z. Just plot the data points, not the line. Okay. And you're going to look at what frequency is the total impedance minimized. It should be at the resonance frequency. Okay. And you'll see here that the maximum voltage might not be, probably aren't at the resonance frequency. The maximum voltage across the capacitor and the inductor are not at the resonance frequency. it might be hard to see because the resistance of your circuit is going to be small. And so there's a lot of analysis in this lab. That's why this lab is very long. I mean, this version of the lab is much shorter than the one we do on campus. The one we do when we're on campus has, you measure the phase angle between the power supply and the voltage across the resistor. So let me show you. I did show you this last time. So this is my special scope that has two inputs. You're only going to have one that has one input, so you can only monitor the power supply. I can monitor the power supply and the voltage across the resistor at the same time. And I have the frequency set to almost resonance. So you notice that the peaks come at about the same time. But then when I go to a very high frequency, you can see the phase shift. Here the inductor is dominating. And then when I go to lower frequencies, let me change the time scale here. Here the capacitor. The yellow is the power supply, the orange is the voltage across the resistor. But here the capacitor is dominating. Okay. This part you're not going to see in the lab. And I can't, one thing you might ask is, well, why can't I use a scope to actually go from the power supply, look at the voltage across the power supply, and then look at the voltage across the inductor, the resistor. It's just that they might not be triggered in the same place. And so you're not going to get any reading for where the peak occurs. So you can't really use one scope in two different places. You actually have to have one scope with two different displays on it, because then they trigger at the same place. Okay. Questions or concerns? If you're using graphical analysis, let me switch views here. If you're using graphical analysis, you're going to have to define your curve fit for the current, because the current looks like this. And you can make, you don't want to have too many. The problem is how many fitting parameters do you want? Because you want to do a fit for this data. How many fitting parameters do you want? I can make this a fitting parameter, this a fitting parameter, this a fitting parameter, and this a fitting parameter. You can try that, but you might have a hard time doing the curve fit. And those of you who are using side data, there's actually a function built in. There's actually graph is built in. It's called a Lorentzian. So graphical, if you plot I versus omega, then in graphical analysis you got to define. You can either define this as a fitting parameter. Since you measure the resistance, you can make this a fixed number. You don't have to make it a fitting parameter. But ideally you want this to be a fitting parameter. Okay. This one, since you measure directly, you can just put the value in. So I'll put a question mark. This has to be a fitting parameter. This one's a must. Because what you're trying to do is use this curve fit to find the peak of your graph. So some labs were done with Davis. We talked about it earlier this semester. I'll show you Davis again in a minute. I think when we did the Ohm's Law lab, because that's the only other lab we did graphing this semester, I went through and talked about Davis. So I would say no more than 3 curve fitting parameters. So in graphical analysis, there's a thing that says define fit, and you have to type this in. So if I were you, I would type this in, because you got to do something like this. I would call that a fitting parameter. I would say A star X over whatever this value is. I'm just making that number up. I would type something like that for graphical analysis, if you're using graphical analysis to do this, okay? And I would type it in Word first, because if you make a mistake, you have to retype the whole thing. So I notice I did this with 2 fitting parameters. Like I said, I don't want more than 3 fitting. You shouldn't use more than 3 fitting parameters. You can always make this B or B squared, however you want to do it. It's up to you. Sometimes when you make it B squared, it'll tell you B is a negative number. But it doesn't fit, it tells you where the resonance frequency is. Because you have a lot of data points, if you pin this peak down well, this should work out well. Now, if we use Davis, let me show you Davis. It's almost like it disappeared from my computer. Give me a second here. Somehow that program disappeared from my computer. Anyway, let me go to the website. If those of you who forgot about Davis, let me go to the website. Davis is a graphing program that you can use. And if you go to the Ohm's Law Lab, we talked about this package. I have instruction. I have an instruction. If you go back to the Ohm's Law Lab module, I have instructions for Cy Davis, and you can download the files. For a Mac, you want to use the beta version. For a PC, you want to use the MSI version file. So this is for the PC, the one that says MSI. And then for the Mac, it's a DMG file. And you can plot anything with this thing. I think one or two of you on the Ohm's Law Lab actually use Cy Davis. And it works well. If you use graphical analysis, you got to use the old one that we used on campus. If you go to the website and use it, the new version that you get from your website is no good because it doesn't do the curve fitting parameters. You do want to use the old one if you have it. Otherwise, you want to use Cy Davis or some other ones. You want to use a curve fitting software that gives you the curve fitting parameters and the uncertainties. I'm not sure what happened to the Cy Davis on my computer. It almost seemed like it disappeared. I'll have to go over it next time. I apologize for that. I don't know what happened to it. Who used Cy Davis this semester? I forget.
I just use graphical analysis.
Okay. Okay. So just make sure. Just make sure that you use the old version. So it was on the Mac?
Yeah. I don't know where it is.
It doesn't. I think it was the second time it disappeared. On my PC, it didn't. It doesn't disappear.
I probably have to re-download again.
Yeah, at least it's easily available. I don't know why it disappears.
Yeah.
But it works nice. I mean, to make graphs. So you can use, I mean, whatever you want to use, just use, but you have to define a curve fit. Unless inside of it, you can use something called a Lorentzian fit, which is built in. Okay. When I talk about this lab next week, I'm going to solve the differential equation and talk about the quality factor and all that good stuff. I'm not having you plot the power for this lab just because we're online. That's the other thing too. We also have you plot power versus omega. Okay, so are we all okay so far? I assume yes. Okay, good. I like the thumbs up. All right. So you do have a lab. I know a lot of labs are kind of bunched up right now. Finish the DC motor lab by Wednesday, and then the transient circuit lab by next week, and then the work on this guy. Okay, what I want to do is briefly talk about transformers. And I'm going to disconnect my camera and connect my microphone so you can probably hear me better. So I want to talk briefly about the transformer. And of course, my discussion about the transformer is highly idealized. It would take me maybe a whole class period to actually go through the details of a transformer. There's a lot of sophisticated, well, I wouldn't say too sophisticated, but there's a lot of complicated ideas that you have to think about in analyzing a transformer. We're going to look at the idealized case. Okay, that's typically what's done in an introductory course. So what I show you here is a schematic of a transformer. You have a source, which is on the left, And you connect it to this device that has two coils. It has a coil wrapped around usually an iron core on one side and then a secondary coil on the other side. And it uses the idea of mutual inductance to induce a voltage on the right side that you see there. So the left side is called a primary. The right side is called a secondary. The right side is where you connect your load to, whatever you want to connect to. Your right side just is designed to make the transformer work. The transformer works on the basis of Faraday's law. A transformer will not work with a battery unless you decide to put a switch in it and turn the battery open and close the switch repeatedly. And then the transformer might work, okay, for briefly. But the transformer requires a time-varying current because it involves Faraday's law. Now, because you have a coil around a piece of iron, okay, and another coil on the other side of the iron, you will have inductors, you'll have mutual inductance, you'll have resistance in your circuit. You also have impedance of your power supply. So the analysis is very, very complicated. And then if you have a load, your load might have an impedance, not just a resistance. So to analyze it, you have to model it somehow. So you first draw a circuit that shows the source impedance, maybe the resistance in the primary, the inductance of the primary, the resistance of the secondary, the inductance of the secondary, and your load impedance. You can combine them into a single circuit that you see below. And you can analyze that circuit. Of course, it would take me a while to analyze that circuit, so we're not going to look at this circuit. I'm going to make some simplifying assumptions. I'm going to assume that my resistance in the primary side is low compared to the impedance, meaning that the current on the primary side is going to be 90 degrees out of phase with the power supply voltage. It's just too much, for this class, it's probably too much details for us to actually analyze it. And then the iron, the ferromagnetic properties of the iron makes things even worse. Now, of course, I can talk about a transformer that's just an iron core, that's an air core. So for example, if I have my coils, I don't have my coils with me. Hold on a second. If I had basically two simple coils with no iron in them, so I hook this up to a power supply, and then this is next to it, so maybe I have them hooked up, set up like this. All the flux through this coil goes through this coil. And so when the flux changes through my big coil, the little coil is going to have a changing flux too, and it'll be induced EMF. And so this can work as a transformer too. Anything with the mutual inductance can work as a transformer, but the transformer itself, it's called a transformer because it's designed to maximize the energy transfer between the primary and the secondary. But if we put iron complicates things very much. So because of its magnetic properties. Whoops. And then you also have eddy current losses in the iron that cause problems too. And we're going to ignore them. We're going to say they're small. So they're highly idealizing the analysis. So here's my list of simplifying assumptions. No eddy losses in the primary. And the flux through the primary, all the flux in the primary goes through the secondary. which is which is very idealized. We're assuming all the flux lines through the primary go through the secondary. And that's what that's the purpose of the iron core in a transformer, is to make all the flux line go from the primary through the secondary. And we're going to assume that the source resistance, the power supply resistance in the primary, is much lower than the impedance of the primary. So that the power factor is 0. And this ensures that P average is 0 on the primary side. So let me draw a picture. So I'm going to draw a coil. And this goes to some power supply. And usually you put an iron core around. And then you put a secondary coil. And then you can put a load here. This could be a speaker, for example. Could be anything that requires a transformer. And I'll tell you why in a minute why you would use a transformer with a speaker. It actually would be between a speaker and an amplifier. So we let omega L dominates. Which means that on this side, V of the power supply minus L, well, I shouldn't say LDI, let me write it this way. The number of turns in here times d phi dt is equal to 0. The number of turns on the primary side. This is the time rate of change in flux. Okay. So what happens on the secondary side? On the secondary side, we're going to assume that all the load is resistive. We're going to assume everything on this side is resistive. Okay, whatever load that we put on there will be basically that of a resistor. Okay. So if we have everything going through, the flux, all the flux from here goes through here. Then the induced EMF is going to be N2 d phi 2 over dt, d phi over dt. That's going to be the induced EMF here. So if V of the power supply, the primary, is N1 d phi 1 over dt, and this is going to be d2 n d phi 2 over dt, then V1 over V2 can be easily shown to be equal to N1 over N2. Right, if I take this over that, I get V1 over V2 equals to N1 over N2. So if the number of turns in the secondary is bigger than the number of turns in the primary, then the voltage across the secondary is higher. We say that is step-up transformer. So if N2 bigger than M1, then we call it step up. If N2 is less than N1, then we say step down. By the way, if a transformer, I mean, I can run the transformer either way, right? I mean, I can make N1 the primary, or I can make N1 the secondary. It doesn't matter. Okay, so this actually can work either as a step up or step down transformer, depending on which side of the transformer I hook up my power supply to. Also, when you actually set this up and you run this, there's actually a very small current going through here that actually produces the changing flux. The current that's going through here, because of the big impedance in the primary, you have a small current, which we call the magnetization current, which is producing the changing flux. That current is small, and in fact, if you actually put a light bulb in that circuit, it would be very dim. But if you then put a load in the secondary, let's say I short this, now you have a big current here that changes with time. Well, if you have a big current that changes with time here, you have a magnetic field that changes with time here, that's going to induce an EMF back here. The problem is the voltage is fixed by this power supply. And so what happens is the current increases. So let me show a demonstration of it. I had Tyler made a video of this. Oops, that's not the one. 1 second, I gotta find it.
So in this demo, we're talking. So in this demo, on the right, there is a
Hold on a second, I will start it up
variac
again.
attached to a 500 turn coil in series with a light bulb, a 100-watt light bulb. On the other
Sorry about that. Let me start it up again. So here's a transformer. Here's the, on one side, on the right side, I have the primary with the light bulb, and on the left side, you have the secondary.
So in this demo, on the right, there is a variac attached to a 500 turn coil in series with a light bulb, a 100-watt light bulb. On the other side is a 23,000 turn coil attached to a rheostat and a single pole switch. You can see that the light is fairly dim, but once a load is applied to the other side of this coil, with a switch, the light gets very bright. I can throw the switch again, and it goes dim again. Please see your instructor on how this works. Thank you.
Okay. Oops. Let me close the window.
So,
Okay. So anyway, so that kind of shows you what happens with the transfer. You don't get...
So when you flip the switch, it connected the coil and the transformer?
Yeah, on the secondary side, you just had a small resistance with a big current in it. And that induced, because of the changing flux, it wanted to induce an EMF in the primary side, but on the primary side, the voltage is set by the power supply. And so what that does then is increases the current in your loop.
Oh, okay.
And that's why the bulb got really bright. Because normally the current's actually kind of low on the primary side. All right, let me go back to the PowerPoint. Okay. But yeah, we are talking about an ideal transformer. So like I was saying before, with no load in the secondary, you have a very small current in the primary, and that's what that light bulb showed you. And that the induced EMF, the ratio of the voltage of the primary to the secondary just depends on the ratio of turns. This is the ideal case. You can get transformers to be 90% efficient, but you don't get them to be 100% efficient. This assumes 100% efficient, and you're assuming that on the primary side, all the impedance is due to a reactance. But like I said before, when you put a load in the secondary, then a current is induced. And then the total current in the primary side is whatever's induced plus the magnetization current. Now, since there's no losses in a transformer and energy has to be conserved, then I1 delta V1 has to be equal to, and I should have put deltas here, sorry, has to be equal to I2 delta V2. So then I1 over I2 is equal to delta V2 over delta V1, but we know that that's equal to N2 over N1. So that's how the current's related. You step up the voltage, the current has to go down. You have to conserve energy. And these two currents are 180 degrees out of phase, and the reason why is because when you have a load here, you're going to have an induced EMF because of the current in this load, and the primary wants to oppose that. So the last thing I want to talk about, like I said, because everything is idealized, I can't see anything in too much depth regarding the transformer. If you have a load in the secondary that produces a current, okay, let's say you have a load in the secondary that produces a current. Obviously, well, let's put I2 on this side. Or I1, sorry. So if I have a load here, this current is just delta V2 over R, and I'm just assuming a resistive load. Okay. If I want to replace on the primary side some equivalent resistance, because I know that I1 is delta V over R1, if I want to replace everything I have on the primary side with an equivalent resistance, then delta V over R1 is equal to delta V2 over delta V1 delta V2 over R2. I should put, or RL, sorry. I may call this the equivalent resistance. Then the equivalent resistance is equal to delta V2 squared over delta V1 squared sorry, 1 over the R equivalent is delta V2 squared over delta V1 squared times 1 over RL. If I take the reciprocal of this, and this is just the ratio of turns, remember this is the load resistance, and so this would be the equivalent resistance on the primary side that produces the same current. So if you want to maximize the energy transfer to your load, you want to have your the resistance on the primary side equal to this. This will maximize energy transfer to the load because this is the equivalent resistance of the circuit. So if you have an amplifier and a speaker and you want to maximize the energy transfer to the speaker, you actually put a transformer between the amplifier and the speaker. And you use this to determine the equivalent resistance of the system. So basically, you determine the equivalent resistance of the system, and you know this ratio. You can actually calculate. You can actually get maximum energy transfer to the speaker. Okay. All right. And so there's not a lot of interesting problems on transformers. Because number one, we're assuming they're idealized. Number two, the expressions are simple. Really, you need to understand that simple equation. You need to understand this simple equation. These are the ones you really need to understand. This one and this one. And just remember that this assumes that on this side, everything's dominated by the reactance. Okay. Most of the problems we do in this chapter are basically you play around with this equation or this equation. Are we okay?
Yeah.
Okay. Questions in general? Well, what about questions on the homework, I guess, because I got email regarding questions on the homework.
It's due on Saturday, right?
Yes. I can add a couple days, I guess. I can change it because the other class asked the same thing. Although the other class I can only add 1 day, but you guys I can add maybe 2 days if need be. Some of the problems take a little while, so just be aware of that. Okay. Like there's a problem with finding the full width at half max for the power, and that might take a little bit of work. So don't wait too long to get started on the assignment. Because if you get it done over before Thanksgiving, that's nice. Then you kind of have a break, although you have a lab due, so that might be hard. No questions, concerns? We're all doing okay? We're all hanging in there?
Yeah.
Okay. All right, so I don't have anything else to say, and I think next Monday, I'm going to go through the differential equation for the circuit and come up with the solutions to it. Okay? All right, then. I guess I have nothing else to say. You guys have a great Thanksgiving. Or if I might see you in office hours.
Thank you.
All right.